Okay, guys, I'm going to talk you through your mock, your exam. Go through a couple of the mark scheme answers with you. Some of you haven't done this yet, so I'm going to hold off posting it until you've all seen it and done it. So let me see that first page there. Okay, as long as this is recording, I can't see the webcam as it's doing it, so I'm hoping it's all going to be okay. Right, so the first one there is, which engineering process would be used to make the crankshaft? Well, the crankshaft is forged. You know that welding is the joining of metals together using a filler rod and some high temperature or electrical current. PCB manufacture is the manufacturer of printed circuit boards and electronics. And riveting is the joining of flat pieces of metal. We've been through this. The right answer there is forging. Which engineering sector would produce the fuel? Now, the fuel as a liquid is a chemical, so it's going to come from crude oil, right? And don't get confused, because it's a diesel engine, don't think that it's going to come from the automotive. It's a chemical process, so it comes from the chemical sector. It's a little bit awkward me flipping these pages over. Okay, match the two products to the most appropriate engineering sector. There's 2 marks available. There's 2 pictures, 2 sectors. Some of you drew lines to every one. It would all be marked wrong, okay? The bonus of this is when it's done online, you cannot choose more than one, right? That belongs to one of those sectors. That belongs to one of those sectors. You can't get this wrong online by selecting multiple. Okay, it'll deselect for you. The cardiac pacemaker is part of the biomedical, and the helicopter rotor blade is aerospace. It's a helicopter, it goes in the air, aerospace, not automotive or communications or chemical. Okay, you've got to know your sectors. Okay, so this one stumped quite a lot of people because they were linking this to sectors as well. All right, now this is not linked to engineering sectors. This is types of engineering operations. This can be carried out. State 2 types of engineering operation that can be carried out using this type of industrial robot. It's with 2 marks, and it just says state 2. So you're fine. We're just stating 2. There are boxes there which you'll just type in, okay? So this robot here, robotic arm, can do assembly tasks. It can pick and place parts on a production line for a car. It could surface mount components in PCB assembly. It could be used to inspect or check. And I think further along there's a question about that somewhere. Pick and place, packaging and dispatch, or some of you did mention handling hazardous, hot or cold or difficult, heavy components, okay? Handling components, assembling components. If you put handling, assembly, if you've done spot welding, assembly of cars, car body parts, panels, that's also fine, okay? 2 marks, state 2. Okay with that? Here we go then. Give one disadvantages using this type of robot when making small batches of products. You don't really have to link it back, right? It's only worth 1 mark. It says type your answer in there. The programming involved in that robot to do your task would be quite time consuming. Okay, so the time and the energy and the effort that's gone into that to do the small batches, you're not really going to get the value out of that robotic arm by doing a small batch. Okay, so the frequency of reprogramming for different batches is going to be an issue. So that's a disadvantage. Okay, high setup and maintenance costs. So it takes you ages to set it up and get it done, and then you run in a small batch off. The reprogramming time between each batch outweighs the point of having it. Skilled labor needed, high cost, initial setup. The health and safety considerations are not always immediately visible. Okay, the high setup cost and the high purchase cost of that to run the batches, you've got to have a specialist person to come in and reprogram that. Okay with that? easy one for most of you. I think we had a lot of good results on this one, okay? Which of these products is from the communication sector? Smartphone. It's not a bridge, it's not a fighter jet, it's not a steel washer. Despite there being a radio or a communications device within that fighter jet, it is not from the communication sector. Okay. Complete the sentence below. Pocket calculator, select the word from the drop-down menu. On the computer, again, you would click that and you'd have these here. So just circle which one. The pocket calculator is an electrical or electronic device. 2 marks awarded there. Now, this one stumped me a little bit, and I had to confirm with Mr. Watkins about this, okay? I thought, and I think I've told some of you, which is my mistake, that piezoelectric transducers are very, very small. They're like little buzzers in some respects, okay, that sense sound waves and sound movement, okay? And they're used for ultrasonic testing and force measurement. They are not for hardness testing. And like what I thought they would be the same too, from the same sector. See, force and hardness are the same too, but it's ultrasonic and force measurement, not hardness testing. So if you did put that, then unfortunately it's wrong. And if I did tell you that, which I think I might have got confused, it is wrong, okay? So I've got that bit wrong. Done that. Now, quite poorly done this question, and some of you were trying to just do one-word answers for this and thinking that it's hard, it doesn't rust, is going to cut it. You ain't going to get 2 marks for that, okay? Explain one advantage of using titanium for dental implants. Some of you put that they don't rust. Yeah? Well, why? There is no danger of infection, right? This is what the mark scheme says. There is no danger of infection. Because titanium is an inert material, it will not rust or corrode over time. Yeah? It's an inert material. You've got to put that down. Put that back on. Okay, implants can be very small. Titanium has a great strength to weight ratio. Okay, they're very small things. They get drilled, you drill into the bone and they screw that in. It can't react with the bone, it can't, it's got to be an inert material. Dental implants will last a long time because titanium maintains its high strength over time. There is no danger of infection because titanium is inert and it doesn't react or get affected by chemical, acid or corrosion agents. Like if you drink orange juice and things like that and your mouth is full of saliva, the acids in your mouth will break down food and plaque and things like that around your teeth, and then you don't want that to react with any of that, okay? Dental implants will not give problems with MRI scans. Titanium is non-magnetic. If you ever had an MRI scan, you wouldn't be able to have any metal on you at all, okay? Because it uses magnetic fields. And if you have implants, if you have pins in your broken arms, elbows, whatever, screws, they're titanium, they're not magnetic, okay? 2 marks. This one, again, I think you've all forgotten what the lathe does or what the lathe is. Give 2 advantages using turn-in techniques to make the machined part. Type your answers in the box. The part's round, okay? It lends itself to being turned. The part is perfectly round and concentric, so components can be produced round, concentric, yeah, cylindrical. You get a good surface finish with a little machining needed, additional machining, sorry. Turning allows for round concentric components to be produced, able to produce size dimension required for the tight fit or tolerances for the application, can carry out all operations if CNC turning centers are used. So if you used a CNC lathe on here, it could be completely automated. Can produce stepped surface required for the seals. So these surfaces here, you just change the tool in and have a step on it. Repeatable products can be produced. If you use a CNC lathe, if you use a lathe and you're skilled enough, you can make the same product over and over again. Can be produced very quickly if a CNC turning center is used, okay? Give one reason why cutting fluid will be used. Well, cutting fluid is a coolant, okay? So the spindle or the cutter speed can be increased, so you can increase the speed and use the coolant to cool the tip to reduce friction, which obviously reduces heat, reduce tool wear due to the friction, reduce the cutting force required, enables greater depth of cut, to lubricate the tool or workpiece, to prevent corrosion. Instead of just, it's a cutting fluid rather than just water. It's not water. It's a cutting fluid. It's more like an oil-based coolant, like the antifreeze in your car. Improved surface finish and helps remove the swarf or the debris from the cutter. As you've been using the lathe and you cut something, you get a build-up around, say you were parallel turning that there, you get a build-up around that area. It will remove that quite nicely for you, okay? Again, done quite well, this question. As you're welding, arc, TIG or MIG welding, you've got to wear a welding mask. You wear a welding mask because the arc or the spark that comes off when you're welding is very bright, so it protects your eyes. So it prevents blindness caused by welding arc, prevents damage to the eyes because the mask has a UV filter. The mask can protect the face from burns because sparks can occur and fly off the material. So, you know, it's no good just having goggles on your eyes because you need face protection as well, okay? The hair can be protected from burning as the helmet fits over the hairline, and the filter can be changed to suit varying different types of welding, okay? Now, characteristics of powder metallurgy. I showed you a video of powder metallurgy. Powder metallurgy is almost like a kinetic sand, and we've discussed this in class, whereby we had kinetic sand and you squash and you compact it. It still comes apart and can be broken, but I showed you a video, and there's a video online for you as well, whereby they produce a mold and they have powdered metal of different properties, different types, and they squash and compact them into molds, okay? It uses a lot of energy, so it's not that one. High tolerances can be specified. It's making the same mold over and over again. Because it's powder and material, it's an additive manufacturing process, so there's no removal of waste. So there's very little waste and there's high tolerances. You can't really do large components. Normally gears or cogs and parts for cars, you know, lots. Ductile components, no. Large components, no. Little waste and high tolerances. Lots of energy used, okay? Because you've got to go through a sintering process, which cooks or bakes the part and forges it, almost melts it together, right? Okay? Right, the turbine blades. Now, this is a turbine that's inside an aeroplane engine. It's a jet engine, okay? Explain 2 reasons why super alloys are used to make the jet engine turbine blades, okay? So the super alloys are a combination. They're the best parts of different types of material alloyed together. An alloy is not aluminium. Okay, I've said this to you before. An alloy is a mixture of 2 or more materials. And what they do with the turbine blades is they get a mixture of 2 or more materials, and they take the best properties of those 2 or more materials and make them into one new material that is really strong or really durable or really resistant to heat or hot and cold. It doesn't shrink or creep, they call it. Okay, let me just go through the mark scheme for this then. The turbine blades will remain stable. These spin, by the way, okay? Because superalloys have high creep resistance due to single crystal structure. So the material isn't like a pure metal. It won't have impurities in it. It'll be a good, solid, and one single crystal structure. Okay. The turbine blade will not fail or exhibit fatigue. Fatigue is like when it gets tired or it wears out or breaks, as the superalloys have a high fatigue resistance. The turbine blades will not suffer surface degradation or corrosion, as the alloying process gives them good corrosion or oxidization resistance. Okay. Again, going on that creep resistance, the turbine blade, when it's on the ground, it'll be quite hot. When it's running, it'll be hot. But as it goes into the air and then comes back down, it heats and cools up, and it's got to be resistant to those changes in temperature. All right. The turbine blades will not deform because superalloys have high temperature strength properties. Okay. This one, I don't know what some of you are doing. Kevlar tires. This is like a stab-proof vest, Kevlar. We've discussed Kevlar as a composite material and the weave. And it's talking about mountain bike tires. And obviously you talk about punctures. You don't want to get punctures. And if it's like Kevlar in your bulletproof vest or your stab-proof vests, it resists a knife. Well, it's going to resist thorns and things like that. So that's why it's used in mountain bike tires. Carbon fiber is used in aerospace applications because of its superior strength to weight ratio. We've done this in class. I've shown you videos on carbon fiber, on fiberglass and Kevlar, and how it's matted and made up. Okay, so it's good, excellent strength to weight ratio. This we need to do a lot more work on. Quite simply, it's poka-yoke. I've shown you a video of that, and there's a video online. You need to look for that. We'll cover all of these areas in a little bit more detail because I got a funny feeling they're going to come up again. Okay, poka-yoke, which is failure proofing or mistake proofing. It's a Japanese terminology. We'll cover that again. Okay, but the answer to that is poka-yoke. Now, this will actually show you a video. This describes what the video is here, but you obviously can't click play because it's on a bit of paper. When you do your online test, you'll be able to click play and you'll be able to see what the process is, okay? This process here is it says which scale of production will be used to manufacture the DVD blanks. The video shows an automated process. Well, if it's automated, it's going to have machines doing everything and it's going to run for a long period of time, and it's not going to be batch. Because further back here, we had the robot arm question, whereby we had batches and we had the issues around disadvantages using this industrial robot working small batches. So you're not going to have a robot working continuously to do small batches. And here, it's the same. Continuous. It's not going to be one-off. One-off is a bespoke piece. Jobbing is like batch and cellular is like batch. Okay, so it's continuous production. This question here, done quite badly because you've not read the question very well. Explain 2 ways. So it's explain 2 ways. So 2 marks for each explanation in which BTEC Engineering, that doesn't matter because that's just the company name, okay, can make its engineering processes more energy efficient when producing this industrial shaft. So what they need to do to make it more efficient is not produce so many, maybe. Yeah, maybe the company is producing loads and they don't need to. Maybe they're overproducing. So they could use a just-in-time manufacturing process whereby they only make enough shafts to supply the market. Then they haven't wasted time or energy producing something that's just going to sit on the shelf. Okay, there's a forging process. It says there, the forging requires a lot of heat and a lot of pressure. It needs to be heated up and stamped as a drop forging, or a forging needs to be hammered. But it needs heat. So could they find a new way of heating it, or could they maybe take the heating process out, and maybe they could use CNC machines instead of forging? Okay, removing that forging process. Maybe if they keep the forging process in, maybe they could reduce the heat lost. Maybe their forge isn't very economical to run. Maybe they could get a new way of running it. Maybe they could run the forge on renewable energy. I don't know. Get a heat exchanger above it. Suck the heat from above that's going to escape naturally anyway, and use that to maybe heat some water to heat the boiler for washing hands or for running the heating system in the factory. Okay. Use sensors during production of the shaft so that the heating and the lighting process switch off when not in use. Talking there specifically about the factory itself now. Use energy regeneration. So, the energy that could be lost during the manufacturing process there, they could recover or recoup somehow. Use CNC and CAM software to reduce the cycle times and reduce the energy. Manufacturing batches to overcome the start-stop issue and the shutdown, and that forge will take a long time to heat up. So if you don't shut it down and restart it, you're saving energy, obviously. Anything I missed on that? Maybe use like solar panels on the roof of the factory to light the factory instead, and look at the factory itself, not looking at the part. Okay. Nice easy one there, but some still got it wrong. PV panels and a water heater. That water heater there is on a roof. That's painted black, it's full of water. The water that's in there gets heated up because the sun shines on the black veins of the radiator and warms the water up. It doesn't get it boiling, but it gets it warmer than cold water. That water then is fed into a boiler system, and then obviously the water that goes in is higher, so the boiler's got to work less and burn less energy to get that water up to temperature. These are just photovoltaic cells, photovoltaic panels. See these on roofs of houses and in fields, south facing, to get as much energy as possible. Flying through this, happy days. Oh, look at this, CNC. This is a CNC measuring device. Where have we seen that before? Well, couldn't we use a CNC, computer numerically controlled robot there? What does this say? To measure and check. We mentioned that, measuring and checking in there. Explain one advantage of using CNC measuring device to check the size of the finished part. It's only worth 2 marks. CNC measuring devices are quicker than conventional methods because it can carry out multiple measuring operations. What it is there's a probe, and it'll be a play button. The video shows an automated probe entering the screen and measuring the components. So the probe would come in, it would touch a point, it would move, it would touch another point, and it would see whether those 2 points are in tolerance. It would touch the end and see if that's in tolerance, and then it would scan the length and then drop down and touch the next point to see if that's in tolerance. It would measure the angle on there, and it would physically map out or draw out the part back to the computer. So where you've drawn that on a CNC, on a computer numerically CAD package, CAD package, the probe would check it against the original part. So this has been made on a CNC, it's put in a jig, okay, and then the probe would come along and it would touch certain points. All right, this light is doing my head in. Okay. Humans can make errors. So if the robot is doing it, the robot's not going to make, or the CNC is not going to make a mistake. It can help speed up the process, and the measurement data can automatically be downloaded and analyzed. So if those parts are out of tolerance and it's coming off a CNC machine, then there's something wrong with the settings on the CNC, or the cutter might be blunt. So it would periodically check these parts and then feed back into the system, and the CNC would flag up an error with the CNC. The CNC measuring device can operate in a controlled environment, enabling highly precise measurements, protecting humans from hazardous environments. Very few mistakes will be made, and it's automated. So once it's set up and it's ready to go, you've just got to drop a part in, press a button, and away to go. You can go and do something else. So it speeds up the quality control process. 4 marks for this one. Now this is about TIG welding. This is tungsten inert gas. Now we've got to cover this. We've got to cover this because I haven't done enough on welding. Okay, you've got MIG, which is metal inert gas, TIG and arc, which is stick. We're going to cover these again, okay? But TIG requires careful positioning of the filler rod as it's melted into the weld pool. So the filler rod is inserted into a high temperature and it puddles and pools it up, okay? It's a very, very slow process. It doesn't generate a lot of heat, but it does generate a lot of light. Would only be economical for specialist applications due to the availability of less complex and cheaper, faster methods of joining, okay? It's not used on massive products. It's not used out in the field for welding pipes in fields or sewerage or drainage pipes or anything like that, okay, or on a building site. It would be used as like a contained, like bike frames would be TIG welded, alloy canisters for cars, compression cylinders, things like that, okay, but small amounts and small products. All right, so the 2 disadvantages, you can say careful position of the filler rod as it's melted into the pool. TIG welding requires precise arc control, otherwise the fusion of the part materials will be poor. TIG welding requires experienced welders because the welds are small and the material is often very thin. It does not generate smoke, so welders are more susceptible to arc eye, so that bright light is a problem. TIG welding would only be economical for specialist applications. And the welding requires very accurate edge preparation for quality joints. So the edges can't be all chewed up and rough cut, as it were, okay? The eye, the bionic eye. Now, it says, bionic eyes are used to help people see. Explain one other way bionic eyes can be used. So bionic eyes could be used to help control movement for paraplegics. So they can send electronic messages to the brain or to prosthetic legs or limbs. So if the paraplegic person who cannot move their limbs or their bodies wanted to, their brain could communicate with this electronic device, which they can do, then this electronic device can communicate with the electronic device on their legs or as a prosthetic limb or arm and move. So the eye sees it, the brain senses the eye seeing it, the brain then tells it to move, and it'll move via a computer bit of software. Okay, bionic eye can be part of a whole body control system. It can be linked to other electronic control devices. Can be used to transmit vision or signals to allow other users to gather or display data. Could be used in high risk areas where you wouldn't want to send a human, but you want to get video data back. You could put it into a robot. You could put it into you could attach that to special goggles that people wear, yeah, for surveying crimes or for recording CCTV, as it were. Yeah. Okay. And this is the last question, and was done quite badly. You guys have got a massive box here, and when you're doing the exam, you'll just fill that box. You'll just keep writing. But it's on about energy generation from photovoltaic panels. It's not asking you to say what the company do now, right? It's asking you to evaluate the possible outcomes from the LCA. Some of you didn't know what the LCA was, and I've done a video on that, and I've sent you links. It's the life cycle analysis, right? So the life cycle of the product would be the collection of the raw material and the extraction, the material production, the production of the parts, the assembly of the photovoltaic panel, the use of the panel, and then the disposal and the recycling. Now, you've got 6 elements there that you possibly could have talked about. Sunny Days Engineering. Let me read you a model answer then, right? Using the life cycle assessment could allow Sunny Days to improve the sustainability of its products by changing the way it extracts raw materials. It could find a more suitable material. So instead of using aluminium for the frame, maybe it could use plastic. I know you don't know that, but you're just surmising. You're saying what the life cycle assessment or analysis will throw up. Could find a more suitable or sustainable material to have a lower environmental impact. It may not be feasible to use that material from a cost or manufacturing perspective. Okay, it may find changes to the assembly process could use less energy. Well, that sort of goes back to that shaft there, doesn't it? Where's that one? That there? What does that talk about? Saving energy? Doesn't it say make it more efficient? Well, this is what this process is here. Making that more efficient. So removing a process or changing the process to make it more efficient. That's what the life cycle analysis would do. Could use less energy. Therefore, the product would waste less. Okay. However, it may mean that energy needs to be consumed elsewhere in the process, e.g. during the manufacture of the panels. The use of the panels saves energy, which should be balanced against the energy used in its production. It's pointless having those panels made using the most elaborate and expensive methods if the energy they use to make them will not be offset or recovered in the lifetime of their use. Does that make sense? Because if you're making something that's designed to save energy, if it costs you £1,000 to make it and energy burnt up is high, you're not going to sell it for a lesser, and you're not going to have it working less efficiently. It's pointless having it. The LCA may also find more parts that could be reused or recycled. However, the disassembly and recycling of parts may be difficult or costly. So when they're making this, they're better off having a product that they can take apart easily, that they can disassemble easily. Okay, so the impact on sustainability of the product, improving sustainability of each of these processes, should be weighed against the cost issue involved, and the environmental impact of each stage will be weighed up against possible benefits. Okay, so you're talking there, and the main points you need to use are the raw material extraction as to where it's going to come from, the material production. So how is that material being refined? Is it being bought in? Where is it being bought in from? Could they buy it from somewhere closer? Yeah. Reduce the carbon footprint of the material. The production of the parts. What processes are being used, or, what processes are being used in the machinery to make the product? Could they be changed? Could they be altered to make them better? The assembly. Are you using humans to assemble it? Are they using robots? Are those robots using energy? Is that energy coming from a renewable source? The use of the product. So is it efficient? Does it need cleaning constantly? Could they use a different type of glass to make it less prone to dirt settling on it? Yeah, put a nano coating on it of some sort that protects it from like a wax or a polish on a car, but make sure it lasts a long time, yeah? And the disposal and the recycling. What happens to these panels once they've been disposed of, or once they've reached the end of their life and they need to be upgraded? What are you going to do? Okay with that? And we'll cover that again in lessons. There's a few things we need to pick up on from this paper. Please watch and listen to my dulcet tones, and maybe we'll take some of the information from that into your unit, into your other Unit 1 stuff, whereby you're going to do another mock, which is the online version 1 and 6, and then we'll get you ready for Christmas for sitting the real exam. Okay, thank you.